All right, so again, we're gonna cover 3 little lessons today. All right, all in Unit 3. So we're looking at this thing called exponential and logarithmic functions here. All right, we're looking at exponential and logarithmic functions. We're going to cover lesson 3.1, 3.2, and 3.3 here. All right, and depending on time, we might get to 3.4. If we do, awesome. If we don't, not a huge deal here. All right, to give you an overview of what's going to be, what you're going to be responsible for tonight. All right, in 3.1, you have 1 mandatory quiz, 1 extra credit practice opportunity. All right, so 1 mandatory quiz, 1 extra credit opportunity. In 3.2, you have 2, smaller quizzes that are broken up. Okay, 2 smaller quizzes here, and then in 3.3 there is nothing. Okay, so at this moment here you've got three quizzes, 3 quizzes and 1 extra credit opportunity here. All right, and then obviously if we get to 3.4, there's another quiz and an extra journal, which is extra credit. But let's see how far we get here. Okay. So if we look at our overview here, all right, again, it's on exponential and logarithmic functions, this entire unit. So you can watch this video here. They reference material from it later on, so we'll watch it together.
What happens when you or a loved one gets sick? What might have caused the illness, and what might you have to do to get well again? Imagine getting together with all of your friends, and all of their friends, and all of their friends' friends, and all of their friends' friends' friends. You get the point. Like putting rockets on rockets on rockets on rockets. Exponential growth is all about going faster, faster, faster. From infectious outbreaks and nuclear reactions to medical treatments and computer algorithms, exponents and logarithms are essential for living in the 21st century. Logarithms are the inverses of exponential functions, and just as important, logarithms help measure tremors deep within the earth. Your wireless devices use logarithms to find the strongest Wi-Fi signal. Exponential and logarithmic relationships are everywhere in the world, and understanding how they work will help you make wiser decisions about your job, your health, and your environment.
Okay, awesome. And yeah, they are really used in a lot of places. They're used in more real world situations than some of the other functions that we've dealt with here. And that's just because of kind of some of the natural reactions or natural processes that we've uncovered. All right, so hopefully you realized that when they were talking about outbursts or outbreaks, right, that works for COVID too, right? And not saying that not saying that one way is better than the other here, right? But they were able to figure out that, bacteria does the same thing, right? So bacteria has this exponential growth here, all right? And again, you can argue which did we do? Did we uncover a mathematical equation that was already pre-existing, or did we make a mathematical model to explain the real world that we observe? Right? But regardless, it's something that, again, is found in quite a lot of places, and people have really utilized them because they found, obviously, like they said, there's a lot of real world examples here, or examples in the natural world, right? Natural or real world here. So people tend to like working with these functions here. All right, and he gave you a prequel here. You've got exponential and logarithmic. All right, and those guys undo each other. Right, they said those are the inverse functions. All right, so we'll take a look at what those mean here. All right, and before we can get started on either one of those two specifically, we got to deal with this thing called geometric sequences here. All right, and with geometric sequences, what it is it's a sequence that we can uncover that uses numbers. All right, it's a sequence that we can uncover using numbers. All right, and I know that that's not a very good definition here, so we'll get a little bit more into it. But for this first example here, all right, you can see that there's 2 ways for winning a prize, right? If you win a contest, you can win every week, You can win $2 multiplied by that week forever in your life, or you can win $2 raised to the power of that week, right? You can win $2 raised to the power of that week. All right, and obviously one of these is going to get much, much quicker than the other one. All right, and that's because it's what's called, again, this geometric sequence, right? So it's a specific sequence. It is a specific type of sequence here that we're going to talk more about. Okay, and hopefully you're noticing here that prize 2 would get much, much larger. And again, this is going to be our geometric sequence here. All right, so if we look at what this means here, all right, so they go to another example here about stairs. All right, they go to another example here about stairs, walking upstairs, and it being a linear function. Okay, and then they want to introduce us to this special name called an arithmetic sequence. Okay, an arithmetic sequence, because obviously we're looking at geometric sequences. So before we identify that, we've got to identify something that we already know, right? Like a linear function, but we haven't been using this terminology here of this arithmetic sequence. So if we look at what this formal definition is, all right, it's a sequence in which the difference between consecutive terms are constant, right? The difference between consecutive terms are constant, right? So each term is found by adding the constant difference to the previous term. All right, so if we have a linear function here, all right, if we have a linear function, and what they're saying here is walking upstairs, right? That's, I don't know why that's what they pick as their linear equation there. All right, but they're saying, okay, when we walk up the stairs, you're adding 1 to the previous number. Okay, when you take 2 stairs at a time, you're adding 2 to the previous number. All right, so regardless, both of those are going to be linear functions or give us in a linear equation here, but it's a part of this thing called an arithmetic sequence, because like it said in the definition, all right, it's the difference between terms is constant, right? So if we look at this second one here, we're taking 2 steps at a time, all right, our difference between each step or each term is going to be this value of 2. Okay, it's going to be this value of 2. And each term can be found by adding the constant difference to the previous term, right? If you're on step 4, you take 2 more steps, you're on step 6, right? So again, adding consistently, all right? Adding consistently. All right, and then this question saying, which way could you get up faster, taking 2 steps at a time or skipping 1, then 3, then 7, and so on? Okay, so if we look at what the answer that they give us there, oh gosh. Okay, is obviously we'd get up the stairs faster by skipping 1 step and then skipping 3 steps, then skipping 7 steps, right? Obviously this would get much, much faster, much quicker. All right, so we're going to look at what kind of relationship is that, and obviously, hint, hint, nudge, nudge, it's going to be this thing called a geometric sequence. All right, but regardless, when we're looking at this step example, okay, it's part of this thing called a sequence. All right, and the formal definition of a sequence is just an ordered pattern of numbers. Okay, it's just an ordered pattern of numbers. All right, and when we're dealing with sequences, okay, we're going to deal with this subscript n. All right, and they italicized it here, so it may or may not be italicized, but it's going to be this lowercase n here when we're dealing with a sequence. Okay, and what that's going to do is it's going to represent a particular whole number. All right, and we've been using this before, but basically think about it like a variable. All right, it's basically a variable here, but it's always going to be a whole number, and it's going to tell us how many numbers away in the sequence are we. Okay, and using this new notation of subscript n, all right, we have this explicit formula, all right, where it is a formula that defines the nth term for a sequence only using the index n. Okay, so it's going to tell us in terms of nth terms, right? So keeping it general, instead of saying the 3rd term or the 4th term or every possible term, right? What we say is we say the nth term, right? The nth term. All right, and again, what that means there is if we're using the nth term, we're using any potential possible term of this sequence here, right? It's going to be a general sequence only using the index n, right? So let's take a look at what this means here.
A sequence is a function, and a function usually involves a rule that tells us how to match elements of the domain with elements of the range. When it's not very obvious what number should come next in the sequence, we need some kind of a rule or formula to be able to figure it out. While not all sequences can be defined by a formula, many sequences do lend themselves to formulas. How do we write a formula for a sequence? Let's look again at our sequence in a slightly different way.
Okay.
We consider n to be the element of the sequence we want to find, while an is the number that we are looking for.
All right. So again, n is what we're looking for. Okay, we're looking for our first term, second term, third term, whatever. All right. And a of n, this is saying, basically what it's saying is a is a value for our nth term, right? So this is what it means when it says subscript n, right? Sub meaning lower or below, right? So a to the n is like saying 5n, right? It's like saying 5n, all right? Because we're going to multiply by our number term here, right? Since this is the relationship, it's 5 times the number, the term, right? 5 times the number that the term is, okay? When we say a sub n, this is like the value that we get out for our nth term, all right? So when we're looking at this, if a of n is equal to 10, all right, a of n is equal to 10 for the second term. All right, so our value of a of n or just our value is 10 for our second term. All right, and that's how you can read this here.
In this case, we find the nth term by multiplying n by 5. So we define an by writing an equals 5 times n. This is called an explicit formula for the sequence. When we have the explicit formula for a sequence, we can easily find all of its terms. If we want to find the 12th term of the sequence, we simply set n equal to 12 and calculate the answer, an.
All right, so again, very hopefully simple. When we have the equation, which is what he's saying, it's pretty obvious as to what this relationship is here, right? And hopefully, even if we didn't have this equation, we could take a couple points here and find a relationship pretty easily. All right. That's if we have this thing called an explicit formula. If we have a recursive formula, all right, that is used to describe the relationship between a number in a sequence and the following number, all right? So again, if we're looking at the formal definition, it defines a term in terms of one or more of the previous terms. All right, so we're going to look at 2 terms that are side by side, basically. All right, so if we look at this here.
There's another way we can write a formula for a sequence. Let's look again at our old friend an equals 5n. In this sequence, we can see that each term is found by adding 5 to the term preceding it. We can express this in another way by writing an equals an minus 1 plus 5. This is called the recursive formula for the sequence. In a recursive formula, after the first term, each term is dependent on the terms preceding it.
Okay. So again, it's using the terms before it, right? It's using the terms before it to figure out the next number. All right, and this would be an example of like our stairs potentially, right? What stair am I on if I'm taking 2 stairs at a time? Well, I don't know. What stair were you just on, right? Oh, I'm on the 6th stair. Okay, well, 6 plus 2, I'm on the 8th stair now. All right, so that's another way of doing this here. Okay. So then here, if we look at this, it's saying how do you generate the sequence 3, 6, 9, 12, 15, ... to get the next value. Okay, this one is obviously going up by 3. Okay, so we could say here, to calculate our value of a, right, a of n is equal to 3 times n, okay? But if the sequence shifts down by 2, right, we're still adding 3 here, right? We go from 1 to 4 to 7 to 10, but we can no longer do this 3n notation, right? So we need a different way to describe this relationship here, okay? So we'll take a look at how to answer that question.
An explicit formula for an arithmetic sequence is AN equals A1 plus N minus 1 times D, where D is the constant difference between terms. Let's see why this works. If this is our arithmetic sequence, then the first term in the sequence, A1, is 1, and the distance between consecutive terms is 3. To get the second term, we start with 1 and add 1 times 3, which gives us 4. To get to the third term, we start with 1 and add 2 times 3, which gives us 7. To get to the fourth term, we start with 1 and add 3 times 3, which gives us 10. Notice that each of these numbers is 1 less than each of these numbers. So we can generalize. To get to the nth term of our sequence, we can start with A1 equals 1 and add n minus 1 times 3. This gives us our explicit formula for this arithmetic sequence.
All right, and notice here, okay, notice here that it's kind of similar to our original equation of 3n here. Okay, we've got a 3 times by an n factor, right? But we've got to take into consideration that obviously we shifted down by 2, right? We shifted down by 2. And we're starting with a number here of 1. But obviously the difference here is still going to be by 3. All right, so that's why we're still going to multiply by 3 here. All right. And essentially what we're doing here is by doing this n minus 1, okay, by doing this n minus 1, we're accounting for the fact that we shifted down by 2, but we're still starting at our value here of 1. Okay, we shifted down by 2, all right, but we're still starting at our value here of 1. So by subtracting 1 every time, okay, we're accounting for our shift down there.
This same pattern works for any arithmetic sequence. If we know the first term, A1, and the difference between consecutive terms, D, then to find the nth term, we can use the formula AN equals A1 plus N minus 1 times D. Let's practice. What is the explicit formula for this sequence?
Okay, so take a look here. All right, we know our first term is 1 there. All right, we know our first term is 1. Okay, then if we look at the difference between them, okay, hopefully you can notice between 1 and 7 is 6. Between 7 and 13 is 6, right? It's going to be a constant difference of 6 here. All right, so what we can look at then is we could plug in those values and check for any nth term here. Right, so if we wanted, we could plug in for our third term here and see if we get out a value of 13 to check it.
The first term is 1. The difference between consecutive terms is 6. So the nth term is given by AN equals 1 plus N minus 1 times 6.
All right. Okay, and again, this general equation here, all right, this general equation, like he said, is going to be good for all arithmetic sequences, okay, for all arithmetic sequences, all right, and even the ones where a of 1 might be 0, right? If it starts with 0, it should still work here because, again, we're not multiplying by a factor of 0, right? We're just adding on to it, right? We would just be adding on to it, all right? So if we look at this here, okay, find the explicit formula. Okay, I'll leave that one for you guys to try on your own here. But again, making sure that the biggest thing I think is making sure that the difference between terms is consistent throughout the values that you're given. All right, that's going to be a big thing here in noticing if it's geometric or if it's, or if it's arithmetic. Right, is noticing that this right here in these 4 numbers, there's a consistent difference of 4 here. right? There's a consistent difference of 4 here. So that's going to be, again, really, really important. Okay, so obviously then when we look at stuff, all right, we looked at graphically what this means and how do we look at this here. All right, so just to remind us here, when the function is not linear, it might grow faster, okay? It might grow faster. So if we look here, we've got a linear function, okay, obviously, and then we've got a nonlinear function. All right, and this is one of those standard nonlinear functions that we looked at, and obviously you can see it grows much, much faster than this linear function, depending on where we're looking in the graph, right? So at the point 2, 2, right, it almost looks like, again, imagine with me here, it looks like it's close enough that at 2, 2, these are going to be similar values, right? And even before this value of 2, right, at maybe 1.5 or 1 or 0, right, it looks like this linear function here, this linear function might actually have a higher value than the nonlinear function. All right, so again, taking into consideration, what is your field of view? What are you able to actually look at here? Because obviously, as we get out to a value of 4 here, this is going to be 4, 4 for our linear function. All right, well, we don't even get to a value of 4 here in our in our x direction because our y has shot up drastically. Okay, because our y has shot up drastically. So again, making sure you take into account all fields of view here. All right, and obviously we talked about this here, but while the line and the curve from the previous page both increase from right to left, the curve increases at a higher rate. Okay, other words, x increases much more quickly than the y does. All right. All right, so again, noticing that one is going to increase much faster than the other. All right, and that curve function on the right that we looked at is a special kind of nonlinear function. All right, I guess maybe we didn't talk about it since we're saying we're going to talk about it. I think we definitely touched on it in pre-calc. Okay, but it's a special type of nonlinear function, and we'll learn more about it later in this unit here. Okay. So then finding a common thread here. All right, so we're going to look at these kinds of functions here.
Here's a different kind of sequence. What do you think comes next in this one?
Okay, so we go 1, 2, 4, 8. Okay, it looks like we're doubling every time. So this should be 16.
What do you do to come up with 16? You multiplied the previous answer by 2, because in this sequence, the pattern is to multiply one term of the sequence by 2 to find the next term. This is an example of a geometric sequence. In a geometric sequence, instead of a common difference between consecutive terms, there is a common ratio.
Okay, so again, this is going to be the difference between our geometric sequence and our arithmetic sequence. All right, in our arithmetic sequence, right, it looked like it was going to be an add 1 situation, right? So this should have gone 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, all right? But obviously we doubled every time. We went from 1 to 2, 2 to 4, 4 to 8.
Another way to say this is that a sub n plus 1 divided by a sub n is constant for a geometric sequence. This common ratio is called R. Look at these examples of...
Okay, so pause there. I know that was a lot. Okay, so if we look at one of our values, okay, so if we look at, let's say, the first term here, a sub 1, the first term, all right, we look at the next term, all right, so we put the next term in our numerator here over our first term, right, or the term we're looking at. Okay, and what this is going to do is it's going to give us this constant ratio. That's what we're dealing with here, this constant ratio. All right, and this ratio being the value R. All right, this constant ratio R here. All right, so that's what we're going to be looking for, is what is the ratio of our new sequence.
Ratio is called R. Look at these examples of geometric sequences and try to identify the common ratio. In this sequence, the common ratio R is 5.
Okay, and you could have done that for any two values. So they picked A3 and A4. All right, if you would have picked A2 and A3, 50 over 10 still gives us this value of 5. So does 10 over 2, right? It's gonna be a constant ratio here, right? So instead of adding by the same thing, right, we're going to then now multiply.
In this sequence, the common ratio R is 1/2.
All right, and again, I personally always struggle a little bit with fractions. Okay, so again, this is a really simple way of figuring out what the ratio might be if you're dealing with unknown things, right? So again, you just put one term over the other, right? So you look at A4 and A5 or A2 and A3, right? But that's the thing is they have to be terms that are side by side, and the term that comes first in the sequence is in your denominator here. All right, the term that comes first in the sequence is the denominator. All right, so then if we look at classifying sequences, okay, we can have arithmetic, geometric, or neither. All right, we can have arithmetic, geometric, or neither. All right, and so this is where it might get a little bit confusing here. So if we take a look here, 1, 4, 9, 16, 25. All right, 1, 4, 9, 16, 25. All right. That's not a pattern. All right, I looked, I tried, right? It's +3, then it gets to +5, then +7, right? That's not a relationship that we know, right? So that's neither arithmetic or geometric. But if we look at something 1, 4, 16, 64, that's going to be geometric there, okay? Because if you look, it's multiplying by 4 every single time, right? It's going to be multiplying by 4 every single time, all right? But if I look at something like 2, 4, 6, 8, 10, 12, okay, that's just adding 2, right? That's just adding 2 every single time, all right? So I'll let you play around with figuring out what the rest of these are here, okay? But again, the difference that I mentioned to you earlier, right? The easiest way that you can figure this out is to look at the terms and to make sure that whatever pattern you think you are noticing, whether it's add 2, multiply by 2, right? Multiply by 5, divide by 2. Okay, whatever pattern it is you're noticing, you have to make sure that it's consistent amongst all of the values here, right? You have to make sure it's consistent amongst all of the values, okay? So that's going to be hopefully pretty helpful here. All right. Now, when we're looking at geometric sequences here, okay, obviously we would like to have a general formula that we can always reference here. Okay. So what we're going to do is similar to our other formula for our arithmetic sequence. Okay, we're going to have it in terms of AN. All right, we're going to have it in terms of AN. All right, but our equation's going to shift slightly. So we're going to have A1 times by R, which is our ratio, to the power of n minus 1, right? So it's got the same parts that our other sequence did. But obviously, now we're not doing addition, right? We're doing multiplication, right? We're raising it to the power of things, right? So our equation has shifted here, right? We have our A1 factor multiplied by our ratio to the power of n minus 1, okay? N minus 1, where again, n is the number of term, right? The term number that we have, all right? So if we're dealing with A3, that's saying the third term in the sequence. That's saying the third term in the sequence. So 3 would go there for our n factor, right? 3 would go there for our n factor. All right, if we're looking at A1, right, our first term here, okay? We have r to the power of 1 minus 1, all right? And let me remind you, if you take something and you raise it to the 0th power, that gives you a value of 1, right? That gives you an output of 1. So r to the 0th would be 1, right? It'd give you a value of 1, and that should make sense here. A1 equals A1, all right? But let's look here at this building a formula video here to see what else they have to explain for us.
Why don't you see why this works? Begin with the following geometric sequence. You can see that the first term, a sub 1, is 3. You should also be able to tell that the ratio between consecutive terms is 2. The first term requires no multiplication. To get the second term, start with 3 and multiplying by 2 one time, or 2 to the first power. To get the third term, start with 3 and multiplying by 2 twice, or 2 to the second power. To get the fourth term, start with 3 and multiplying by 2 3 times, or 2 to the third power. Notice that each of these numbers is 1 less than each of these numbers. Now you can make a general statement. To get to the nth term of the sequence, start with a1 equals 3 and multiplying by 2 to the n minus 1 power. This same pattern works for any geometric sequence. If you know the first term, a sub 1, and the ratio between consecutive terms, r, then to find the nth term, you can use the general formula shown here. Why don't you practice? What is an explicit formula for this sequence? The first term, a sub 1, equals 1,000. The ratio between consecutive terms is 1/10.
Okay. And I'll let you continue to do this for the sake of time. I want to make sure that we keep moving here. All right, but again, the biggest thing here is figuring out what is the relationship between the factors here. Okay, so immediately I know he told you that it was a exponential, or he told you it was a geometric sequence here. All right, but if you didn't know, the first thing you'd have to do is look at, okay, is it going to be arithmetic or is it going to be geometric? Am I adding or subtracting by the same value, or am I multiplying and dividing by the same value? All right, and obviously you should, something should click in your head here and be like, okay, well, it looks like I'm dividing by a number. Okay, let's see if it's the same number. Right, and you should test a couple points here, right? You should test a couple points to see if the ratio is the same. All right. At least my rule here is test 2 different places in the values that you're given. So personally, I would have checked 1,000 and 100 like they did, and I maybe would have checked this 1 and 1/10 here, right? Just to verify. Okay, so again, it's about finding what the relationship is between the values. Okay. So then here, again, it takes a little practice to notice the various parts of geometric sequences. All right, but once you get it down, it's going to be consistent here. All right, and I will let you guys try these on your own for extra practice. All right, but all right. Make sure you read the instructions, okay? Make sure you read the instructions, because it says, for example, type 0.7 instead of 0.7, okay? And I know that I messed that up when I first did it. I kept trying to put 0.7 because, like you, sometimes I forget to read instructions, okay? So I'm highlighting it here for you. All right, type in 0.7 instead of 0.7. All right, and you can type in fractions in the form that they show you there. All right, but again, it's figuring out what are the different points here. Okay, what are the different points in this relationship? Okay, so first off, they want you to look at A1 and R. Okay, once you have those relationships, or once you have this relationship and you understand what the first term is, okay, you can write our general geometric expression, right? You can write the general geometric equation and use it to then solve for A5 and A10 here, okay? All right, you can use it to solve for those extra values. All right, and again, it's going to be repetitive. It's the same process over and over again. It's just picking different values or having a different, a different relationship there. Okay, and what we're going to do here is we're going to look at then what does this look like in terms of a graph here. Okay, so we started looking at that linear equation, and we started looking at that graph that grew really fast. Okay. And we're going to look at this animation here.
Just as the graph of any arithmetic sequence in a series of disconnected points that follow a straight line, the graph of a geometric sequence will follow the path of any exponential function. For example, the graph of the sequence in the first example will look like this. In this sequence, r is greater than 1, and the graph is similar to that of a function that shows exponential growth.
Okay, so again, remember, exponential growth went up, up, up really quickly. All right, and again, it looks 3, 9, 27, 81. Obviously, it increases really, really quickly here. All right, so geometric sequences, I hope you caught that have a relationship that is greater than 1, right? That has a relationship that's greater than 1, right? These numbers get larger. They're going to look like this here, right? It's going to have some kind of shape like this.
What shape do you think the graph of a geometric sequence will have if r is less than 1? In this geometric sequence, r equals 1/2, and the graph is similar to that of a function that shows exponential decay.
Okay, and that's what he's saying here, exponential decay, right? So it goes down very, very quickly. All right, and we'll work a lot more with that later in this unit here. Okay, so don't freak out about these graphs here. All right, but what you would need to know is that we can graphically represent these equations or these sequences here by just plotting them on the graph for the different values that we get. Okay. And hopefully you noticed or were able to see here down here, our value for our x component was just the number of term in the sequence, right? So A1 was plotted at location 1, A2 was plotted at 2, A3 plotted at 3. All right. So just a couple tricks here. All right. Then what we do is we can represent them using this thing called sigma notation. Okay, using this thing called sigma notation. All right, and when we would use this here is when we wanted to add terms together. Okay, if we wanted to add terms together. All right, so if we look here, right, 3, 6, 12, 24. Okay, so this was our geometric sequence. Okay, it was the common ratio was 2 there, right? So we were going to multiply everything by 2. Okay, so, sorry, hiccups. So these individual numbers here were our sequence, okay? But what we can do here is we can add this sequence together, all right? We can add this sequence together. All right, and there's plenty of practical uses for this here. All right, but what you can do here is, again, you can add them together, and we can write it in this thing called sigma notation. All right, and obviously we can scroll over these different parts and look at what they mean. All right, but hopefully you notice here. Okay, A1 is still our first term in our series, right? So it would still be the value of 3 for this series. Okay, it's still our first term. R here is still our common ratio. All right, R here is still our common ratio. K here is going to be our number of term, right? So if K is 2, we're talking about the second term here. All right, and what this is saying here is, okay, right now K is equal to 1. All right, and it's going to go all the way up to, right, we're starting at K equals 1, and it's going to go all the way up to N here. All right, so that's what this is saying, from K equals 1 all the way up to N. All right, and N obviously isn't a number. It goes on and on and on until we choose it. All right, so K always starts at 1 here. All right, k starts at 1 and increases by 1 each time. All right, and again, k represents the variable of our index. Okay, so we can't say n over n, that wouldn't make sense, right? So we're starting with k equals 1, right, which is our first term, and we're going all the way up to n, which is whatever we decide. All right, and then we can write it as this capital S lowercase n, right? And what that's saying is the sum of our series. Okay, we can also call it the summation. All right, the sum of our series or our summation. All right, so how we read this here is this is saying the sum of our series from k equals 1 to n, right? So from our first term to our nth term, using this relationship of a1, our first term, multiplied by our ratio to the power of our term minus 1. Our term minus 1. Okay, so unexpected error, awesome. Whoa, apologies guys. I just lost my internet there for a second. That's kind of funny. Sorry about that. All right, so if we get back to it here, all right, looking, what we can do here is we can do this thing called sums, right? We can sum up our geometric sequence, right? And rather than taking the sum of every possible number, which would be insane, okay, we can do this thing called partial sums, right? So we can find the sum of a smaller set of our sequence here, or our series. All right, so if we look what finding a partial sum looks like.
How do you find a partial sum for a geometric sequence? Since the nth term of a geometric sequence is an equals a1r to the n minus 1 power, the nth partial sum, Sn, in sigma notation will be given in this way. This looks as if it could get complicated or tedious to calculate the partial sum, especially if n is large. Is there a formula that could help? It turns out that there is a formula. Instead of just showing it, however, let's derive it first. That way, if you happen to forget it, you can always figure it out yourself. Start with a general finite geometric series. Now, multiplying the entire equation by r. Subtract the second equation from the first and watch what happens. Now, factor out S sub n and solve. This is the formula for a partial sum of a geometric series.
Okay, so we go from this rather complicated looking sigma notation, and this is saying our sum for everything, all right, and this is obviously this is how we can curses, sorry, thank you. All right, this is how we can actually calculate it using this generalized equation here. All right, the parts haven't changed. They still represent the same thing. A1 represents our first factor. R represents our ratio. And obviously, to the power of n, n still represents what term we are looking at. All right, but we can now use an equation here rather than having to add them all up individually like we saw on the last slide here. All right, so what we can do here is we can look at this partial sum tool. All right, and what we can do here is we can use it to help us figure out what our sum is. All right, and obviously, yes, you can just plug this into your calculator here, but they thought they were going to be nice. So if we looked at this here, okay, the first term is 1. All right, so our first term is going to be 1. The ratio is 2. And the number of terms is 30. Okay, then the sum of our series. So if I submit this here, this is what it's going to give me out for my S of n. All right, and all it did was it plugged in 1 where you saw A1. It plugged in 2 down here for R and R. All right, and then the number of terms here, okay, the number of terms is still our n value. So we plugged in a 30 there. All right, and all it did was it did the calculation for you. So super simple, hopefully. There we go. All right. We can do the exact same thing for all of these. The first term is 3. Our ratio is 0.5, and the number of terms is 5 here. All right. So you can do that for multiple of these, but all it's doing is it's replacing it right here in this equation for you. All right. Again, being mindful of parentheses and order of operations. Okay. So I suggest the way that you use this, I suggest you do a couple of these problems here and make sure that you calculate in your calculator, right? I would suggest you do this in your calculator, get out your value, and then test it in this partial sum tool, right? Because if you plug these in this form here and you do not get out this 5.813 value, you did something wrong, right? There's an error with the way that you're plugging it into your calculator, right? So this is a really good way of checking yourself right off the bat to make sure that you're plugging in the order of operations correctly. Okay, I really suggest you do that one. All right. Now here is a real world example here looking at calculating our retirement savings, okay? Because we want to retire someday, sure, right? So we can look at this partial sum, right? And this is a really great one because what it's going to do is every month or every year you're going to add in a certain amount of money, and even if you don't want to count it as retirement savings, right? Let's say maybe you're saving up to buy your first car, or you're going to save up for college or something, right? So it's a recurring thing that you're going to put in money into a place, but then at the end of it you want to know the total that you have, right? So if we were going to do this, okay, we need $1,000 per month when we retire, right? Because of inflation, money is usually worth a little bit less each year. To make sure your $1,000 will go far, you estimate that there's an inflation of 0.1, right? Which means that we need to add on 1% for each month, okay? Because we're assuming that inflation is going to cause money to go up, right? So we need to add in more money to account for this, all right? And we plan to retire for 30 years, okay? So we can then solve this problem. Again, pulling out the major pieces that I just did. $1,000 per month is what we need, 30 years, okay? 30 years, but we have an inflation of 1%, all right? So what we're gonna look here is we can then state this as our geometric series, right? So we start with $1,000. Then we have 1,000 plus the 1.01, right? Adding that 1%. Then we square it, right? Then we cube it, right? We keep going on and on and on to account for the inflation cost, right? To account for the inflation cost. All right. And something I'll point out here, the reason you don't just go 1.01 to 1.02, right, is because when we square it, we are now taking into account that we are even further than this guy, right? If we just went to 1.02, it wouldn't be taking into account that this isn't $1,000 anymore. This is 1,000 plus our 1% addition. So you have to have it as this geometric series here. Okay. So then what we can do is state the formula in our partial sum, right? We know our relationship. We know our first term here. Okay, so we can state it in that form by identifying our variables, right? So we know our A1, we know our R value, okay? And then all we have to do is do a simple substitution here. Can we do a simple substitution? All right, and since the values on bottom are easily added together, right, we can divide those out, right? So we get our equation here, our one-line equation, all right? And then what we can do is we just restate our solution, okay? We restate our solution. So for every number of months n, the total needed for retirement is negative 100,000 times by 1 minus 1.01 to the power of n, all right? So that's what we've gotten to as our solution, all right? And what we can do here is take it even one step further, right? We can take it one step further. we plan to retire for 30 years here, which is 360 months. All right. So we can then calculate about what we need to save here, about what we need to save. So you put in a 360 value for our end value, and then we calculate it out, and lo and behold, we need about 3,500,000 in order to retire for 30 years. Right? We need about that much. All right. And then this question here is talking about opposite of inflation. Oh. Something related to saving that works like the opposite of inflation, so which causes money to lose value. All right. So inflation, there is also deflation. Okay, there's also deflation. All right. So deflation would be that you know, it's an opposite, right? So if something is inflated, it's going to get larger. If it's deflated, it's going to go downwards. All right. And then another thing they're talking about here is interest, right? So again, I think we talked about that. Interest helping your money grow, making your money work for you. All right. Again, here's a mortgage problem that I'll let you look at on your own. But again, realizing it's just a geometric relationship, right? They might try to fancy it up by putting dollar signs and using other variables here, the principal P, right? But regardless, it's still just a value. Okay, so I'll let you try that one on your own here. All right. So then, again, if we look here, okay, one, it's telling you it's a geometric sequence, okay? So this is even easier. But again, the first step for me is always make sure that you identify it's geometric, arithmetic, or neither. Okay, that's going to be a big part there. All right. So again, there's a lot of really good problems that you guys can work through. And then if we go to our study guide here, all right, if we go to our study guide, okay, so arithmetic is talking about adding and subtracting in a series, right? And doing it consistently, all right? But geometric is talking about multiplying and dividing, all right? So it's talking about multiplying and dividing, all right? Identifying which sequence or series is, which sequence or series is going to be important here, right? And whether it's geometric or not, all right? For this one here, okay, you're going to write the exact same formula, right? It's this same form every single time, all right? Again, you're just changing the values of your ratio, you're changing the values of your starting function here, but notice it's all in the same form, all right? So then once you are able to figure out this form here, you can then move forward to the next one, right? So you identify the two major parts you need to make your equation. Then once you've done that, you can write your equation and utilize it to figure out the values for A5 and A6, right? Which are just the fifth term and the sixth term, okay? Then we got a little introduction to what that looks like graphically. So again, if the geometric sequence, if the ratio is greater than 1, it's gonna have that growth, right? Where it goes in the positive direction, all right? And if it's less than 1, it's gonna have that decay where it looks like it's getting really close to 0, all right? Then we took a look at this thing called partial sum. All right, so we can add up a certain number of terms in a sequence here, and we can call that our partial sum. All right, and when we're dealing with geometric series here, we can utilize this equation. Right, we can utilize this equation. All right, so really trying those out here. All right, and obviously for the checkup, okay, for the checkup, it's just going to have a lot of practice problems, right? Identifying what those different parts are, okay? And again, obviously explaining in your own words is going to be also helpful, the difference between geometric and arithmetic, okay? Identifying those key parts, what makes it different, and what are you going to notice when you're looking at those sequences or series, all right? Okay, then it's going to ask you to write the first 5 terms here, all right? So again, you can either understand how this equation works here and realize what the relationship is, or you could just plug in the values of 1 through 5 for n here, right? So if n equals 1, what's my first term? If n equals 2, what's my second term, right? Same thing for 5 here. All right, 6 and 7, again, you're given the parts and it's asking you to write the first 3 terms or to write the explicit formula, right? So again, regardless, I always suggest that once you've gotten the parts, you write the explicit formula, because then you can use the formula to help you solve the rest of it. All right, and then for 10 here, really going to be helpful looking graphically, identifying it as geometric, arithmetic, neither. And then if you want to get a jump start on the game here, when you get a geometric sequence, looking at it if it's a decay or if it's a growth. All right. So again, there's a lot of problems here, and I know for the sake of time, maybe you don't want to try all of these, but I would really suggest that when you look at, something like 8 and 9, or I'm sorry, 8 and 9 look a little bit different here, but maybe like 6 and 7. Okay, if you don't want to do both of them, at least do one of them that have this similar kind of question here to make sure that you're touching all of your bases before you get to this quiz here. All right, so you've got one quiz that's mandatory, and then this practice is obviously extra credit. Okay, this practice is obviously extra credit here. All right, then looking at lesson 3.2 here. All right, this is talking about exponential functions. All right, exponential functions. So we just got introduced to what that graph might look like. All right, and to highlight this, okay, obviously we talked about something as in linear growth. All right, that would be having a straight linear line here. All right, but there's different ways that monies can grow. Obviously, if we had the option here, we would want to double our pennies for a month. Oh, it won't let me click it. Apologies. All right, but what you'd want to do is you'd want to double your pennies for a month, and you might not believe me here, but all of a sudden it's going to get really, really large, and it's going to end up being over $1 million. All right, and that's just the beauty of this exponential growth function, right? That's the beauty of this exponential growth function, and right, turns out you'd be $10 million if you chose to receive the pennies. All right. It'd be $10 million if you chose the pennies. All right. But that's an example of this thing called exponential growth. All right. And we also introduced ourselves to exponential decay. That's if we have the same type of relationship, but not in the growth function, in the decay or the decreasing function. All right. So there's this value here of E. Right, and if I click on it, E is an irrational number, okay? It is on your calculator, believe it or not. All right, so if you have your calculator on hand, awesome. All right, if you look at your calculator, okay, in the far left-hand corner, or I'm sorry, the far left-hand column, right? You've got your on button in the very, very bottom left, okay? Above that, you have STO, which means store. And then you have this LN button, right? And we'll talk more about LN later here. But if you look right above LN, mine's in, again, blue, whatever your second color is, right? You can see this E to the power of X, right? E to the power of X. And that's standing for this irrational number E, all right? This irrational number E. And we can approximate E by substituting large values of N into this huge expression here. Or again, you can always use your calculator and plug in the value for E here. All right. But when we look at these 4 examples, hopefully you're noticing something, that all of these have it to the power of X, right? It's no longer X to the power of something. We're now taking a value to the power of X. All right, and so that's what you should notice here with this variable. Okay, it is now, again, we're taking it to the power of our variable. Okay, and if we look at this just to re-solidify some terms here. Okay, again, coefficient A, we can look at this form here. All right, A is a coefficient. All right, A is our coefficient. B is our base, and then obviously X is our exponent, okay? And per usual, our coefficient can be positive or negative, right? But the base B is positive and not equal to 1 here, all right? It's going to be positive and not equal to the value of 1, because obviously 1 to the power of anything is going to give us 1, all right? And so here, again, these are a lot of different equations, and if we look at, just an example here, okay, 2x, or 2 to the power of x, they're talking about amoebas or like bacteria, things in biology. So those grow with this thing called an exponential function, right, that we're dealing with, this exponential function, because they're going to grow 2 to the power of x, right? Because if you think about it, if you start with 2 amoebas, right, hopefully you remember some basic bio here, all right, when they divide, right, they usually make a new cell, right? So if you start with 1, it splits in half, it makes 2, right? And then the 2, both of those 2 are going to go through the same process and then split in half again and make another pair. All right, so you start with 2, you get to 4, those divide again, each of those divide. You now have this 8, then 16, right? And all you're doing is now taking 2 to the power of whatever the number of splits are, right? And obviously it grows very, very quickly here. Okay, and what we can do then is we can look at our things in terms of output values. So if we think about this like an expression here, all right, if we think about this like an expression, all right, you've got your function with our exponential, right, our 2 to the power of x, and we've got our more traditional x squared here, okay? So if we're looking at what these values look like, right? So again, treating it like an input-output situation. If x is our input, f of x is going to be our output. So hopefully you notice here that in our traditional equation, right, it's going to be larger than our exponential when we're in the negative region, okay? But when we start to get into the positive region, what you're going to notice is all of a sudden the exponential gets drastically larger than the x squared here, right? And I wish they would have kept going, but this is going to get drastically larger here than just our traditional exponential. All right, and you can plug in these values and test it out here. All right, but again, this is what we talked about earlier. While field of view is going to be very, very important, because if they asked you which relationship would you prefer for your money, if you only saw 0 to 4 or even 0 to 3 here, you might consider looking at a traditional x squared, because obviously it's the same, if not larger, for most of these. All right, so again, field of view is going to be really, really important. All right, and again, when we're dealing with growth, we're typically calling it this exponential growth. All right, so we can look at this animation here to show things doubling in size. All right, so 0, 4, 8, 12. Right, so this is showing you a representation of an exponential growth. It is doubling. And I like that they kind of made it look like a graph here, because you can kind of see it's got that curved nature to it. Okay, then we could have this thing called exponential decay. It's got the same curved nature to it, but obviously now we're starting at a high value and getting really, really low. Okay. All right, so then we can now evaluate or look at these exponential growth and decay functions, all right? And it's going to have this standard form here. All right, so again, this is another new equation for us, all right? We have f of t, again, function as a factor of t, right? This is our function, y equals a0 times by b to the power of k times t. All right, so A0 is our initial amount, right? So think A0, right, is our initial amount. B is our growth factor, all right? B is our growth factor. K is our growth rate, and T is time. All right, K is our growth rate, and T is time. All right. And in this equation here, A sub 0, B, and K are all fixed, right? T is the only variable because look, it's a function of time, f of t, right? So that means time is going to change. So if we look at any of these examples here, you're going to notice, okay, well, we've got an A sub 0, that's 2. Our base value is 3. And our growth factor, right, our K value is 5 because we've got 5t. All right. So if it asks us to find f of t, right, it's giving us a specific t value. It says find f of 1, right? So it wants us to plug in 1 for t. All right, so we just plug it in and we can solve for our output value at that specific time. Right, we can do that for any of these guys, right? Regardless, they might not look, right? They might not always look as clean, right? Especially again when you're dealing with fractions here, they might not look as clean, but it's the same exact relationship. It all boils down to this value here, and knowing that all of these values are going to be fixed, and the only variable is t here. All right. So then if we look back at this penny problem, okay, we had the choice of picking pennies doubling every day or $1 million. Okay, and the reason again it got to this $10 million is because of this exponential growth. All right, it was an exponential growth, and we found out that again it was doubling our pennies. We started with 2 pennies, and we doubled it every day. All right, we doubled those every day. So what that turns into is this 2 to the power of x relationship. All right, so again, if we look at our general equation here, a times b to the power of x, a is obviously 1, b, our base value is 2. Okay, and then again, x is just the number of days here. So if we have 30, right, at the end, we had 2 to the power of 30, right? We had 2 to the power of 30. Okay, and obviously, again, we could look at more values in between, but this is just proving to you as to why this works here. All right, and again, you have 4 pennies, you double it, right? I go from 4 to 8. I'm gonna double 8, 16, double, right? It gets really, really large rather quickly here. All right. So for exponential functions, right? The variable is now in the exponent, right? Exponential, it's going to be in the exponent, all right? And we have exponential growth, which obviously means we're going in the positive direction, right? It's increasing. And we have exponential decay, which is going decreasing, all right? So again, looking at some of these, just realizing the notation, f of x equals 4 to the power of x. Again, this is saying the function as it relates to this value of x here. So it's saying f of 3, it's telling you plug in 3 for x here. Hopefully not too terribly difficult. All right. And if you need it, if you forgot, right, there is a caret button, right? So how you could plug this into your calculator. All right, how you would plug this into your calculator is 4 caret 3. Okay, you can plug it in like that. If you've got a little bit more advanced calculator, obviously you could write it as you actually see it. So 4 to the superscript. I'm trying to find the superscript button for you. Yeah, 4 to the 3rd, right? But my calculator is a TI-84, so I have this little caret button. And for me, this caret button is found underneath my clear. All right. But again, you could just easily plug that in. So 4 to the caret 3 gives us 64. All right. And again, what that is it's 4 times 4 times 4, which gives me 64 here. All right. Again, same thing here. It's just, it looks like a little bit more complicated relationship than it needs, than you need to worry about though, right? Here's still our constant value is 1/9. Our base value is still 2, right? And our exponent is still with that 2 factor, or that 2 factor. All right, so again, it's asking you what's f of 5. So plug in 5 for x and then solve. right? Again, just being careful with order of operations. Obviously, you have to do this exponent first here before you multiply by your term out in front here. Okay, so you have to make sure you're following order of operations. It's going to be super, super important. All right, I'll let you guys try these practice problems on your own. And now what we can do is we can look at a real world situation of compound interest. All right, so this is going to be really important for you when you're taking on bank accounts or making bank accounts or looking for a new bank account, right? You want this thing called compound interest, all right? And what it's going to essentially do is it's going to add on your interest really, really quickly here. Okay? All right, so it has this formula here of A of t equals P times 1 over Rn, n to the power of t. All right, and if we look at these different values here, A stands for the amount of money that's going to occur in our interest. All right, T is going to be our variable time. P is going to be our principal, which is just the original amount invested. And then we have R over N. We have R over N. Okay, so looking at that guy, all right, and again, it's just picking apart this equation, knowing what the variables stand for. So again, if we had a rate of 9%, it would go there, all right. And so what we can see here is with compound interest, again, we would, again, dissect what these are telling us and plug in our different values. So if we had a savings account that holds $200 and earns 3% interest, okay, we can look at what this looks like after 8 years, all right? And so what that is we would identify our different values. Okay, 200 is our principal. It's the first thing that we invested. Okay, we have a 3% interest, all right? And we know that it's compounded, right? It's compounded monthly, all right? So if we pull this apart here, if we pull this apart, we can find out our different parts. And hopefully what you noticed here is that since it's compounded monthly, right? N is 12 because there's 12 months in a year, right? There's 12 months in a year. All right, we're going to do this 12 times a year because it's compounded monthly. All right, so then once you've identified the values, as I always say, I think that's the most difficult part here. Okay, once you identify your values, you're pretty much set to go. You plug in, you chug through the problem, and you get your final answer here, okay? So then looking at different interest periods, right? So instead of having it compounded monthly, right, we could look at it having it compounded different amount of times here, right? So all right, so if we looked here, 4, right, that would give us 2.44. If we had 12, okay, it gets a little bit larger. If we have 52, gets even larger. 365, it gets larger, right? And so what you're going to notice here, and I know these values aren't super large for any of these, okay, but that's just dealing with if you're starting with $1, right? If you're starting with $1 and you have this compounded interest, if you have this compounded interest at a rate of 100%, at the end of a year, you're going to have $2.7, right? And I know that's not super drastic here, okay? But imagine if you start with more than $1, right? Imagine if you start more with $1, all right? And the last thing I'll say about this here is this compound interest, right? This compound interest, I told my juniors this first semester, but this compound interest is how credit cards work, right? They take your total and they add an interest. And if you don't pay it off, they had more interest on top of the interest they already had. It's how student loans work, right? But on the flip side, it could potentially be how you know, banks and your bank accounts work. So the more money you put into it, right, the more interest it's earning, or the more, you know, money you're gaining, right? So this could be a really good thing or a really bad thing, depending on how you need to use it. All right. So again, just some fun facts there. All right. And now moving on to this irrational number E. Okay. So you can read these facts about E here, but basically, we can use this to help us solve a different type of compound interest problem, okay? And this one is if it gets calculated every instance in time, all right? Every instance in time, all right? So if we look at this here, all right, instead of doing it annually, monthly, daily, okay, it's doing it at every point of the day. All right, and so all we would do here is we would just change, and we would have it be e to the power of our RT value here. Okay, we still have our interest rate, we still have time and our principal, but now instead we are having it to the value of e. All right, and again, e, if you look on your calculator, it says e to the power of x. So you can plug in whatever RT is there for your value of e. All right, so again, if we plugged in here, $100 invested, 7% interest, compounded continuously for 5 years. All right, so again, the key word there is compounded continuously. Compounded continuously. So that's going to tell you you're going to use this equation rather than the equation on the last page here. If it's compounded continuously. All right. So again, all you do though is plug and chug, right? You plug and chug through those values. All right. Again, taking a moment, understanding how to actually plug this in. All right. Plugging this in is going to be super, super important. All right. So I don't know why they showed you this button here. All right, this is a super old calculator here. Most of us are used to the TI-84 or TI-83. So if we look here, perfect. If we look here, okay, it's right there. That button is right there, that E to the X button, okay? So all you would have to do is hit second, hit E to the X, all right? And then it's gonna have it in E to the power of what, right? You've got to plug in a value for X here. So for this guy, it would be 5, right? You would just tug in second, E to the X, 5, potentially close a parentheses if there's an open parentheses, and you just hit enter and it'll give you your value there. Okay. So then if we look at some of these different ones, okay, again, just double check on your calculator. That's going to be super, super important, okay, is making sure you can plug these in correctly. All right. And to finish this one out here, okay, so the amount of money in a savings account with compound interest grows exponentially, right? It grows exponentially. It may take some time, right? It may take some time, but you're going to find out that when you have this compound interest, it's going to be more beneficial for you if you can get that to add on more money for you in your bank account there. All right. And again, the difference between compound interest growing monthly, yearly, right, at these set intervals, or growing continuously. That's going to give you your 2 different equations we need to use. All right. So again, this one here is the first equation that we looked at. If it was compounded monthly, right, or compounded at a different interval. All right. So again, this n value here would be 12 since we're looking at it monthly, right? We're looking at it monthly, it would be 12. All right, but again, identifying the different parts, plugging it into the equation, that's the hard part. All right, so this is the first one if it's compounded at set intervals. Obviously, this one's yearly or annually, which means yearly, right? So that's going to be a value of 1 there. All right. And then obviously if it's compounded continuously, that's where we change when we use this different equation of E. But hopefully you notice it's very, very similar. Instead of the 1 plus our R over N, it's just this value of E instead. Okay, it's just this value of E instead. All right, and this one is definitely a really, really huge one for me. Make sure you do this problem and check, because order of operations is going to be super important on your calculator. Again, I cannot stress it enough. All right, super, super important that you are paying attention to that. All right. If we look at our study guide here, okay, if we look at our study guide, again, it's gonna be your best friend with all of these different equations here, all right? But in general, we can have an exponential function, right? And it's gonna look like this, where again, you've got your coefficient and your base, and it's raised to the power of your exponent, all right? And again, your coefficient can be a 1 here, right? So this could just look like our base to the power of x. Right? A can always be a 1 and just looks like it goes away. All right. Then we have exponential growth and we have exponential decay. So again, growth being an increase, decay being a decrease. All right. Identifying the different parts of our exponential growth function. All right. And this was talking about something in general, right? So if we start with our initial amount, right, B is going to tell us if it's a growth or decay, right? Depending on if it's B can be for either growth or decay, all right? And so can rate, but the rate here, K, is going to be what determines if we're going to increase or decrease, right? Are we going to grow or decay? All right. There's a couple problems here that, again, key is going to be figure out the different parts, all right, and then make sure you have the right equations here. And luckily, they already gave you the equations for both of those, okay? And then we moved forward into our compound interest, all right? So looking at compound interest at set intervals versus compound interest where is it? There we go. All right. That's compounded continuously every second of every day. Okay. Again, really, really good things for us to be able to go through and practice. All right. And then, of course, obviously with the checkup, what's really nice is they gave us the formulas already that we're going to need. Again, being careful with, is it continuously compounded or compounded at set intervals? Okay, that's going to determine which equation you use, right? For the first here, it's not terribly difficult. It's just evaluating the functions, making sure that you can plug into your calculator correctly. And then these guys here are all about your interest. I would personally suggest you choose at least one that's compounded at a set interval and one that's compounded continuously. All right, and then you have 2 mandatory quizzes here. All right, so evaluating exponential functions, right? So the first part of this study, and then the second one here is calculating exponential growth. So you can probably assume it's going to be based on our interest functions, all right? So our continuous versus our interval interest, all right? And finally here for unit 3.3, okay, this is just examples and applications of these exponential functions. Okay, there is nothing you have to do, and I know that we are out of time here, okay, but I would suggest just at least, if you got some time tonight, at least go through these in general so you can see how to dissect some of these word problems, okay? I would, again, suggest at least going through a couple of these, all right, and seeing how they relate to the different problems, because, again, while you might not have a quiz on it in this, obviously you're going to have a unit test, and your unit test is going to have some more of these word problems, these more wordy type problems, right? These are what we call like explaining or word problems. These would be like your multi-tiered questions where it's got like an A, B, C, D, E, F. All right. So again, taking a minute to really go through these problems and try to dissect it. Okay. So we're going to end there. We're not going to get to 3.4 today. So we'll just do 3.1, 3.2, and take a look for me at 3.3. Okay. So again, you have one quiz here, 2 quizzes here, and then 1 extra credit opportunity at 3.1. Okay. So like I said, we'll end class right there. You've got those mandatory quizzes, you've got those extra credit opportunities. And if you guys need something from me in the meantime, please don't hesitate to ask. Like I said, tomorrow we will continue to hit the ground running with those next 3 units here. Okay. Other than that, have a great day, guys. Juniors, I'll see you later. All right. See you guys later. Goodbye.